Okay, we're recording. Hello, students. What I want to do today is to continue our discussion of annuities. Remember, the first week of class, we talked about simple interest and compound interest. And I mentioned the fact that in order to discuss purchasing vehicles, paying off loans, which may mean something like purchasing a home, or maybe you want to make some money. You want to create a sinking fund, so to speak, to finance a college education in the future by maybe 15 to 20 years. So, one thing that's nice about the annuity is that we have a sequence of periodic payments where the periodic payment is constant. Now, there are variations on that, but what we will be doing is actually making periodic payments at the end of each interest period. That's called the ordinary annuity. And again, when we think about that, it's like, okay, we're applying that compound interest to each payment. But then we make another payment and we apply the compound interest, etc. So we've got these payments that just move along just like we did before as a compound interest problem. But now we have more of them. That is, if we're going to think of N as being the product of M times T, where M is the number of compoundings per year, then we could actually come up with a formula if we use the geometric progression. And just remember, I introduced that last week as a segue to this discussion on annuities. So let me go ahead and share my screen. Once we talk about how these formulas come about, then we'll make an effort to look at some of the examples in your lecture notes to provide you more detail. Now, what we're going to find is that, as I've said before, sometimes we like to use letters that we haven't used before just to keep everything very clear. Now, in class, I used an A and a lowercase r in my derivation of the geometric progression because at that point I was just looking to get a formula. Sometimes it's better just to avoid letters that we're going to need otherwise. And for that particular discussion, as you've noticed here, instead of the R, I'm using the alpha, just to make sure that I don't use something that we've already offered as a variable for another formula. So we just want to avoid the confusion. I know in many classes you can have variables that stand for two or three things, and that's okay, but we just want to keep it as simple as possible. So now we will take A to be a fixed positive number and alpha also. Remember, fixed means constant. And then we're going to take N to be a fixed natural number. And thinking about this, N will be replaced with M times T, where M is the number of compoundings per year. So just in order to think about each periodic payment, we're going to write down the periodic interest. So remember, we had I equals R divided by M. And that's what we call the periodic interest. Periodic interest. And therefore, in order to compute the compound interest, we had the 1 plus I raised to a power, which basically gave us the number of compoundings we were applying to the principal. So for now, let R be the periodic payment. And our goal in this case is to move in periodic payments into the future. And I've used an uppercase because we're eventually going to replace the sum with FV for future value. Or as we would say, future value of the annuity. So again, with our construction, the periodic payments are made at the end of each payment period where we apply interest. So the first payment will move n-1 payment periods. Oh, well, let me put in the interest component. Remember, 1 plus I to the n-1. That is, the R doesn't get the power. And then the next payment made in the second periodic period, which is at the end of that period, will now run for n-2 periods. So the idea is that this is simply compound interest applied to each payment, but it's offset by 1 because you move into the next payment period. So if we keep going, the next periodic payment will run for n-3 payment periods, and we just keep going. So we put the ellipsis, and then, for instance, we'll have one that moves 1 period. Well, I'll put in some extra ones so you can see the pattern. 2 periods, and then the 1 period. And then and I'll put a 1 there, and then the very last payment that doesn't move at all. So that's the very last payment you make, and so that's already in the future. So we don't move it anywhere. It's the last payment. So notice here, when we look at this, we have n-1 payments that have been moved into the future. So, and the way to do that is to just see we have R here, and we progress to n-1, and then the additional R here for n payments. So n periodic payments. So the nice part about the annuity is that we do have the mechanism to find out what this amount of money is. And we're just going to call that the sum for now. Notice here, I could have written the sum here for the n terms. I believe that's the notation I used in lecture. So now, if we look at this seems to be a little bit backwards. We can see here, if we compare the two, and I'll write this in red, we see that the A is equal to R, and now I'm using an alpha as the common ratio. We see that's equal to, in this case, 1 plus I. I'll just leave it in parentheses if you like. So now we've got this nice formula. We simply multiply A times the fraction 1 minus alpha to the n divided by 1 minus alpha. So this implies, so this is really nice if we can first motivate the idea of the sum of the geometric progression and then apply that to the actual future value of the annuity. So we have the sum will now be the A, which is R. And then we have the 1 minus alpha to the n. Here's our alpha. 1 minus 1 plus I to the n. And then downstairs we have 1 minus alpha. So we have 1 minus 1 plus alpha. So again, 1 plus I, not alpha. Obviously, this is 1 minus alpha, so the alpha is 1 plus I, so we get this. So now let's simplify. Of course, the numerator is what it is. Lots of letters, just have to keep track of the letters. That's the only hard part of this. And then, of course, what we see when we distribute the negative, the ones absorb and we have a negative I. Now, there's nothing wrong with this formula, but it's a little bit awkward with all the negatives. So what you can do is multiply the numerator and denominator by -1 to get rid of some of these negatives. Remember, the negative times the negative is the positive in the real number system. So we'll just say we have, and I'll write this in, multiply -1, -1, just to make the formula look a little bit more user-friendly. So now we get R times 1 plus I to the n minus 1. So that reverses. And then downstairs, we just have the I. Now, everything about this formula is fine in terms of the periodic interest. We are accustomed to that, and that's a notation we use. We know by definition the periodic interest is just the annual interest rate divided by the number of compoundings per year. So now we just make a little change here. So we're going to set R to be the periodic payment. That's exactly what we call it, but we want to use symbols that give a little bit more idea to what they actually represent. We often in science and engineering, even in mathematics, use variables that give some idea as to what they represent, and that's commonplace. And then, of course, we'll replace the sum of the n terms with what I set up here, future value. So this implies that we have future value of the annuity will just be payment. Now, remember, this might be a little bit awkward. PMT just represents one number, not three numbers in product. That's maybe a little awkward to look at it that way. You're thinking that's not the best use of our letters, but P is usually what we have for present value, and we don't want to overdo that. So we'll just do PMT to represent the periodic payment. Again, if you don't like the notation, you can always change it, but I will assure you that this is fairly standard. And then we have 1 plus I. And also, just as we have up here, as I've noted, replace N with MT. Now, of course, notation varies, and you'll see in the worksheets, the notation varies, but I want to use the letters that I have actually utilized in the lecture. And this is a little bit more consistent. So now we have MT minus 1 I. So we get a nice compact formula for the future value of the annuity. And we see that there's not a lot of difference. The main change, I mean, if we just covered this up, that would look like the formula we had before, but we have this difference and we have this periodic interest in the denominator. So we have to be careful that we actually compute this correctly using good arithmetic skills. And also, a lot of times cleaning up the arithmetic so it's a little bit easier to approximate. We want to write down an exact expression and then with one calculation do an approximation so that we get good numbers. We always want to avoid any unnecessary rounding to keep our computations exact as much as we can so that we give our clients good numbers. Now, one thing that you may see here making the periodic payments will accrue the future value, but maybe you want to flip this around. One thing that's also popular here is that we can actually solve for the periodic payment. So equivalently, we don't get anything new, we just get the formula where we solve for PMT. So we'll invert this fraction and multiply. So payment would now be the future value times, so we have I, and then 1 plus I to the MT minus a 1. So it's a twofer. We get 2 for the price of 1. So you don't have to necessarily write this as a separate formula since it's implied by this one. But it's also good to write it just to make sure when you're doing your homework and your computations that you go ahead and solve for the particular unknown that is requested by the problem, and that way you set up what you need to do initially. There are many ways to work with formulas. You'll always work with formulas in business, mathematics, whatever area you cover. So setting up some type of routine that's consistent is good. So now we've got these formulas for future value, and they will be used uh, quite often. And we think about making money as a positive thing. When we make investments, especially through annuities, we're doing something of this nature. And like I've told you before, the more risk you take, the better opportunities you have to make money, but you can also lose money. So there's a lot of discussion about how annuities play a role in making money, and there's certainly so many different ways to invest money, but this is certainly one that's been around for some time that is well understood. And we'll take an opportunity to work with some of the examples here. But before I do that, I want to go ahead and look at the formula for the present value of the annuity. So we get to use the same formulas. So now we're interested in present value. We'll use the same letters that we had before and then change it up. So like future value, we have FV. We'll do PV when we're talking about the present value of an annuity. But let me just remind us, let's see so we can make a comparison. We have A plus A alpha plus A alpha squared, etc., plus A alpha n minus 2 plus A alpha n minus 1. So we have our n terms here. This is just convention. This is one way to write it. There are many ways to write geometric progressions. One may be more useful than others, but since I've started with this, we'll continue with it. So we have A times 1 minus alpha to the nth power, 1 minus alpha. So that's what we used the last time. Now what we want to do is to move in payments to the present. So move in periodic payments, and we'll use R again, to present day. Again, this construct, though abstract, is exactly what we do. So the abstraction of mathematics works in so many different areas. We often think, well, money's very tangible, but as you know, when you deal with economics and you deal with uh, the movement of money throughout all types of transactions, it becomes a very theoretical construct. And so, even as a business major, you spend lots of theoretical time thinking about money, just like an economics major. So the beauty of the abstraction, though it is more complicated, it simply gives us a vehicle to write good formulas that help us to solve problems and to help us to serve our clients better. So now moving things to the present day is not so bad. So again, we think of being at the end of a payment period. So the very last payment will move forward in a backwards type way. So we actually get a negative power. So we get 1 plus I to the negative n. Now, many students have trouble with the negatives. And so one thing I have many students do is think of it like this. If you like, you could say equals, in this case, R, and then you can write 1 over 1 plus I to the n, like that. And that way it's you're dividing by that particular fraction and it or that term, and so it makes it a little easier to see what's going on. And then the next one will move forward by 1 less power. And if you want, you can put a little dot there. It is juxtaposition gives you the multiplication, but let's just put the dot just to be a little more precise. And minus 1. We'll write another term just for completeness. So we're using the compound interest formula to move to present day. And then dot, dot, dot. So we'll do the second to the last if you want. Plus I to the 2. And then the very last one, that's in the first payment period, but it's at the end of the period. It's got to move forward 1 period. So we have R like that. So the negative power is fine, but it's probably a bit easier to see how the powers move if you think of it with the reciprocal. And you don't have to do this, but this is certainly a way to look at it to maybe make it a little bit easier. So this would be our sum of the n terms. Now, when we look at this, we've got a little bit different construct. We're not going to factorize this. You can, but let's just keep it very simple. We see here, this is the actual A. And so when we get here, we've got to rewrite our very last term so we actually have a better idea of what's going on with the powers of n. So now let's just write this. Notice this particular term, if we take the A away from it, so we have the R, we have the 1 plus I, and here I'm going to write this with the power on the outside. And I'll just have n minus 1. So our last term looks like this, and our A looks like this. So a little bit different from the last computation. So this implies A is actually R divided by 1 plus I, and the alpha in this case is just 1 divided by 1 plus I. So we have a little bit different arithmetic, but it's still the same idea. So thinking of these as reciprocals probably makes it a little bit easier. And then we can move to the negative exponents when we write our formula. So now this implies we want to use this. S sub n will equal A, which is R divided by 1 plus I, times, and now we have 1 minus alpha to the n right here. So we have 1 minus alpha, which is 1 divided by 1 plus I, to the nth power. And then downstairs, we have 1 minus alpha. So this is 1 minus 1 divided by 1 plus I. So this, though the fractions introduce more arithmetic, if we write it this way, it's usually easier to see what's going on arithmetically, and then you can make these assignments with more confidence. There are many ways to write things, and on a given day, one form of how you write may seem fine. The next day, you'll change it, but that's just how you're thinking on a given day. So don't worry how you actually construct things. Just do it in a way that is easy to remember and allows you to make good decisions. So now we can go ahead and introduce the negative power for this. Just go ahead and reciprocate it and get a common denominator here. And we'll actually get a formula that looks very much like the last one. So here we have 1 minus 1 plus I to the negative n. And then downstairs, we just want a common denominator, which will absorb here. So we have 1 plus I. So we have 1 plus I minus 1. So again, the arithmetic works in our favor. The 1 plus i's give us some multiplicative inverses. So these absorb. So we just get r times 1 minus 1 plus I to the negative n, just using the negative exponent for the reciprocal. And then, of course, the 1's absorb here, just leaving us with an I. So now, again, we'll do the same thing. Set R equal to payment, PMT, and SN will just be PV for present value. So again, when we think about this and we think about what we did for the last one, we'll go ahead and add this again, replace N with MT. And I'll just write that. Replace N with MT. So this gives us present value is payment times 1 minus 1 plus I to the negative n divided by I. So again, notice here, we didn't do the minus 1 divided by the minus 1 because we didn't have the overabundance of negatives. So this is fine. There's nothing wrong with this. This works very well. Now, also, you can just think of the fact that we can solve for the payment. So we have payment equals, in this case, PV times, and then we just reciprocate the fraction, 1 minus 1 plus I to the negative n, like that. So now we have, again, let me just bring back the previous sheet. If we compare the two, they look very similar. We just have a difference in the way the compound interest part occurs in the formula. But you see very much the same. So the major difference is just that this particular expression is inverted as it relates to the 1 plus I. And then, of course, instead of the positive power, we have the negative n power. So again, this is what we call the present value formulas. Okay, so now let's look at some interesting ideas. So what I want to do now is look at some of the formulas that we have used in our lecture notes. and to see how they actually evolve now that we have some new ideas. And so first we'll start with the present value. Let's see, let me go over here to, let's see here. Okay, so let me just go over here. Let me not minimize this. Let's go. Where can I go? I can, oh yeah, let me move it over there. They're new rules. They're new rules to everything. And so you don't want to stop the recording. So let me do, let's see here. This I'll minimize and I'll go over to our um, lecture notes. Okay. See, that's pulled up. Let's see if we can open this up. Okay, there we go. Now, what I wanted to do is start with one of the examples in your lecture notes, and I'll make this a little bit larger. Now, this is number 4. I just want to cover several of these and to give you some idea how this correlates with what we did in the problems with the compound interest. Very, very similar. And what we want to do, ladies and gentlemen, is just configure the arithmetic so it's very neat and avoid any unnecessary rounding. So let's look at number 4 here. We see George deposits $75 at the end of each quarter for 40 years into an account paying 2.8% compounded quarterly. Now, as I've said before, lots of times in class, this becomes an academic exercise, and you're thinking, maybe I don't have this much time, 40 years to do this, but just remember these are exercises to give you practice. So don't worry that maybe they don't make a lot of sense for you. Of course, I wouldn't want to be doing anything for 40 years. That would be a little bit ridiculous. So now what we can see is we just simply take the idea here and then decide what is it we want to do. Well, for this particular problem, we're interested in finding the future value of these periodic payments and of which there are very many. So let's just write down basically what we learned from just reading the few words in this problem. The payment, the PMT, is 75. And I've said before, you don't always have to write in the units, the dollar signs or whatever. We know that the measurement of time is via years. So if you want to save a little bit of writing, you can do that. I won't consider that to be an issue. Sometimes I will do it and sometimes I don't, but I'm not trying to be sloppy. I'm just basically focusing on the arithmetic and making sure if we need to change units, we definitely will do that and make sure that everything's consistent. So M, again, quarterly gives us 4 levyings of interest per year. So M is equal to 4. And then, of course, T, the duration in this case is 40 years. So now the actual total number of compoundings, and that's an easier thing to say than levyings. The total number of compoundings will just be 4 times 40, which is 160. Okay, and now in this particular case, we have an annual interest rate of 2.8%. We can certainly write the 0.8 as 4/5. Now write an improper fraction. 5 times 2 plus 4 gives us 14. And then to write the percent as a fraction, we can simply divide, in this particular case, by 100. Now notice here, the 14 gives us a 2 times 7, and of course 100 is 2 times 50, so the 2's will absorb, and we're just left with 7 divided by 5 times 50, which gives us 250. And let me move my projector down, turn this light off. Let's see. Where are we? Okay, just 1 second. Let's see if I can, there we go. There we go. I'll get that out of the way so you don't see me looking this way and that way. Now, notice we can simply take the annual rate of interest, and then divide by 4, which is the M, to write the periodic interest. So now that's just 250 times 4, which gives us 1,000. So we have 7 over 1,000 as the fractional equivalent of the periodic interest. Now, it's okay to write decimals, but one thing that's nice about this is this creates formulas that are easy to work with. And in cases where the decimals would be an advantage, like when you're working on the APEs, the annual percentage yield, that's fine, use those. But here, this makes for a much neater calculation. So now we need the expression 1 plus I. So we have a common denominator of 1,000. So 1,000 plus 7 is 1,007 divided by 100. So that gives us the 1 plus I. So now we have the input for the exponent key. Remember, when you're doing these calculations, you necessarily need a calculator because we're not really using tables to do these approximations. You need a calculator that has the exponent key and also log keys, because those turn out to be very useful. Now, excuse me, for the future value formula, remember we had the payment and then we had the compound interest term minus 1 divided by the what? The periodic interest. So this is very important. Let me bring that sheet back up. And this is where students will make errors. And of course, I'll pull this up. Let me just and stop this share just momentarily and pull this back up for you to see. Notice we have the periodic interest here. And so it's really important to remember this. If you get sloppy, you'll put the wrong term here. So just remember that as you do these calculations. Not difficult, but it can be an issue. So let's go back to our lecture notes. So now what you see is we simply have, in this case, the payment, we have the periodic interest in the denominator, and then the compound interest calculation raised to the MT minus the 1. Now, one thing that you can do is you can actually reduce some of the arithmetic here, and it does make it a little bit easier if you think of it that way. Notice we have the division by the fraction, so the 1,000 can just come upstairs with the 75, and we'll just leave the 7 downstairs. And then notice here I've got brackets. You'll have the 1,007 divided by 1,000 raised to the 1/60th power minus 1. Now, this provides an exact calculation. Now, when you want to approximate this, say you want to work with your clients, you need to do a one stream, as they say, one line of calculation and not do several different streams and then do approximating. The idea is if you need to break down the calculation approximation, make sure all the numbers are not truncated nor rounded. But you can actually do this if you use your parentheses. So you can start out with parentheses to actually compute this, the exponential term minus the 1, then multiply by the 1,000 and the 75 to give you one number. And then divide that one number, which is undeterred, not truncated, not rounded, you divide by 7. And notice what I do here. I just use, as I write my lecture notes, I just use the Google calculator that you have online that's free. There are lots of free calculators. And of course, you can have free calculators for your cell phone, which again, provide excellent resources for no money at all. And then what we see here is we have $21,995 and then an odd number of cents. Now, for these particular calculations, the formatting was to round to the nearest dollar. So in this particular case, we'll simply use the rule. Since we have the 5 here, we can simply move this 5 up to the 6, and then rounding to the nearest dollar will give us 21,996. Now, again, I want to emphasize to you, you do not want any premature rounding when it comes to doing these calculations. You want to have everything exact. So this is exactly why I think it's good to get into the habit of doing your calculations this way. And then you've got nice, clean numbers that you can now input into your calculator to give you a very, very high level approximation without any approximations. And then you can simply format that number based on the directions in the problem. I can't emphasize how important this is. I remember even teaching calculus students with introductory differential equations when everybody's rounding things. I said, ladies and gentlemen, keep everything exact. Otherwise, your answer is going to be very far from the actual uh, good approximation. So it's not just for business majors, it's for any student who actually uses technology to write a good approximation. So now what we can see is the future value, if you can afford to do it, is certainly a good way to make money. But obviously, the higher the interest rate, the more money you can make. But let's just see exactly what George actually was able to do here. If we take the 160 payments and multiply that by the periodic payment, we get $12,000. Okay, so that's the actual amount of money that he was able to put into his investment. And so if we just take the rounded amount and subtract 12,000, we get an interest accrual of almost $1,000, $9,996. So even though this was at a fairly low interest rate, I mean, even though for a savings account, 2.8 would be a gold mine. But this is 40 years. This may have been something for which he wasn't overly anxious about the money, just maybe done as a younger individual, and maybe he forgets about it. And then then he gets a letter in the mail, oh, look, you have this much money. So again, the future value can give you an opportunity to make more money. If you've got a good set of parameters, you can certainly make a great deal of money, and hopefully the risk is fairly low. And certainly when you have banks that offer this, there's nothing certain about anything, any investment or any guarantee that you're going to get exactly what you think you are. And of course, this is a very preset situation where the periodic payments do not change and the interest rates do not change. So of course, there could be adjustments to this. Now, there's another example that I wanted to share with you. Let's see, here we go. Right. This is number 9, and then we'll look at some of the examples with the present value. Now, one thing that's good about these formulas that I might add is you can also look at these in reverse when we actually solve for the payment. You might think, well, there's a certain amount of money that I would like to be able to have in the future. And I have this much time, and this is what the bank is offering. What are my payments going to be? So let's look at this particular example. This is number 9 from your worksheet. It says a fund of $60,000 is desired. What payment must be made quarterly in an account that pays 5% compounded quarterly if the account runs for 13 years? Now, again, just remember whatever the M is, that will correspond to the payment. So the payment periods and the interest periods coincide for obvious reasons. And that's basically how we did our computations. So we're not just overly happy with quarterly. It's just the examples that we have. Clearly, we could have any number for M. I guess some popular ones would be 4, would be semi-annually 2, and of course, probably the most popular would be monthly, where M was equal to 12. So now let's just look. We have a future value of $60,000. That's the amount of money that we would like to have in 13 years. Again, M is equal to 4. And now we've got 13 years times 4. Looks like we're playing cards. We have 52. So there are 52 payment periods. Now, again, the annual rate of interest is 5%. So we can go ahead and write that as a fraction. Of course, 5% is just 5 divided by 100, but 100 is 5 times 20, so the 5's absorb, and we have an annual rate of 1 over 20. Now, just like with the last problem, I may add that depending on the types of numbers you have, things may look more difficult, or at least less user-friendly numbers, but the key is no rounding. Let's write exact expressions. And so we have the annual rate of interest divided by 4. So we just get 20 times 4. So the periodic interest rate is just 1 over 80. And now, of course, we need 1 plus I. So we have a common denominator of 80. So 80 plus 1 is 81. So the 1 plus I is just 81 divided by 80. Now, remember, when we solve for the payment, we have the future value times the fractional part. So we've got the periodic interest, we have the future value, there we have 60,000, and we have 1 over 80. And then, of course, the 1 plus I we've computed to be 81 over 80, and we must raise that to the n, which in this case is 52, and then subtract the 1. So now, again, if you like, notice we have the 60,000 times the 80. And if we look at this, notice this, one of the zeros absorbs, and we just have 8 in the denominator. So we have 6,000 divided by 8, which gives us 750. You don't even have to make these reductions if you don't care to. It just usually makes the computation a little bit easier. So instead of having to input 1 over 80 and then divide by the expression in the denominator, then multiply by the 60,000, it might just be easier to try to combine some of these. Again, that's completely up to you. So now what we see is we have 750 times the reciprocal of this difference. So what we can do, and you can do this, you can use the reciprocal key on your calculator, or you could just do 1 divided by this expression where you use your parentheses. So now we have 1 divided by 81 divided by 80 with the exponent key raised to the 52nd power minus 1. We get that particular approximation. And then we multiply that result by 750 in 1 character string. Again, if you do intermediate calculations, be sure to store all of the numbers. Don't truncate, don't round any numbers in an intermediate fashion. That will ruin the value of the approximation that we're wanting to have for our clients. Now, again, you might be thinking, and if you do take some calculus, you will have some understanding of how series in calculus are actually used to make your calculators work. It's all arithmetic. So the fact that all of these approximations could be computed by hand and put into tables before we had the beauty of the technology to do this more quickly. Again, they still rely on the software, which includes the series, which give us these beautiful approximations almost magically. So just remember that the calculus is responsible for the abilities of your calculators to give you approximations in just no time whatsoever. So now, if we follow the same formatting as we had before, notice I've got several digits here with the Google Calculator. We have 826, and then we have these decimals stringing along. And so again, we're going to round to the nearest dollar. So again, we won't change the 6 because we have the 1 here. So now what we see is we basically have a periodic payment of $826. So again, $60,000, a larger amount of money. And so you're thinking, okay, for 13 years, I'm going to make 52 payments of $826, and I will have accrued $60,000. So again, just like the last problem, you can compare other things here and figure out how much money you actually earned. That's the easy part of the problem, but it's often something that an individual can do. It's like, well, I'm going to need this much money, say in 13 years, you want to have a down payment for a home. Who knows? Maybe you want to buy a particular vehicle, where you're just thinking, I'm just going to save the money and not go into debt. Well, that's a great thing to do if you can do it. So now let's look at some of the present value. So I'll stop the share. And let's see, let me go over here. Let me use the same technique so I don't do anything that will upset Zoom. Okay, so we've done our derivation. So let me make this a little larger. Yeah, your Blackboard Ultra has some really nice features, which are really good. So let's look at an example. Okay, so let's go back to our Zoom. Okay, let's share. All right. Now what I want to do is look at the present value. Now, remember, it's very much like the future value formulas, but the compound interest part and the one get inverted. And then instead of having the positive power in the exponent, we have the negative. So that's really the only difference. Not very difficult, very much like the formula we've been using with those two minor differences, but they're very important ones. So let's look at an example that we have here. We have a car dealer. Again, we're looking at present value, and we're also looking at finding payments when we have a present value calculation. So we've got a car dealer. We have 4.6 annual rate of interest compounded monthly. So in this case, we're using the 12 for the M, which is obviously very popular in our society. We have a trade-in value of $8,000, and we have an additional $1,000 down. Okay, so now we're looking at something that might be very much what you will eventually experience. And then you're thinking, okay, $500 monthly payments for 2 years. Okay, now the idea is this is a transaction that we need to buy a car. Okay, so you would not necessarily do this. You would go into the dealership. You would basically look at what's going on, and they would usually just say, well, the monthly payments will be this, and this is what you're going to have to do in order to eventually own this vehicle. So this problem is a little bit different. Notice here we have $500 monthly payments for 2 years. So this is kind of a problem in reverse. And we're thinking, okay, what is the present value of this calculation? So now let's go ahead and write down everything that we're going to need. We want to compute cash value of the car today. Okay. So you're thinking, there might be many reasons why you would need to do this. But again, just think of scenarios and also think of problems as being academic exercises. So if they don't necessarily make sense to you, just solve the problem. And then later on, you can spend more time on problems that you think are more relevant to your life. So what we want to do is find the present value of all these payments. So another thing that might sound a little bit more realistic to you is if you've already purchased something on time and you come into some money. Maybe you're thinking, I've got all this extra money. Let me run all the payments to present day and take care of this loan. So that would be another way of thinking about what we're doing. So notice we have an annual interest rate of 4.6%. 0.6 is just 3/5. So we can now write the percentage as a fraction. So first we have 5 times 4, which is 20, plus 3 is 23 over 5%. And then, of course, just divide by 100, 23 being a prime number. We can't really do anything with that. That's fine. And now we need the periodic interest rate. So when we look at this, we have the annual interest rate divided by M, which is 12. So now again, 23 being a prime number, we just have 12 times 5, which is 60, and then just tack on the additional two zeros to get the product. So we have the periodic interest rate of 23 divided by 6,000. And then, of course, we always need 1 plus I, the compound interest expression that we always have when we work with compound interest. So we need a common denominator. That's 6,000. So 6,000 plus 23 is 6,023. And then our 1 plus I is 6,023 divided by 6,000. Put a box around that because we're going to need that in the denominator. The idea, or excuse me, we're going to need that in the numerator. And then notice I put a box around this because we need that in the denominator. So the boxes aren't there just to confuse you. It just means they're important and they're going to need to be used later. Now, another thing that's very important, if we have 2 years here and we've got 12, we just have 24 payments that we have to worry about moving around. So now the present value will be the payment, which is 500. And then we have the expression, which is inverted. We have 1 minus 6,023 divided by 6,000 to the negative MT. That's the difference. Remember the negative because we're moving the payments forward. We have a negative power. And then downstairs, we have the value of I. Now, just like I said before, if you like, you can invert because we've got the fraction in the denominator, so you can bring the 6,000 up and pair it off with the 500. Nothing's going to absorb, but as you're doing the computation, this may be just a little bit easier. So now you can think about this character string from 6,000 up to the brackets and compute that first. Again, you don't have to worry about overdoing the parentheses. If you go ahead and compute the numerator and you've got that calculation in your computer, then you can use the division symbol and then put in the 23, and you still get an unaltered approximation. That is, you get one level of approximating. The idea is if we're approximating with every intermediate step, we're ruining the final result. So what we want to do is avoid that. So now, just like we had before, I use Google and I've got 11,443 with several decimals here. But again, we want to round to the nearest dollar. So now, of course, we have the 6 here. So we're going to round the 3 to the 4, and that's going to give us $11,444. Now, yeah, when you think of this, you're thinking, well, what's the cash value? What's the cash value? Now, we've moved the payments forward to present day, or actually backward. We've taken them from the future and moved them up to present day. And also we have our what is it? We've got our down payment of 8,000. Trade-in value, excuse me, and then we have this down payment of 1,000. So when we add to the 11,444, we have a cash value of $20,444. So again, the calculations here may simply be what you need at the time. Again, this is an academic exercise, and it doesn't necessarily mean that you have to compute this. But I will say this. You have at your disposal the ability to work with numbers any way you like. Now, notice here, and this is very important, if you look at the part that was actually in the calculation, you've got 24 payments of $500, which is $12,000. And then you have the present value. So you've only got a little bit of interest, $556. Now, I will say this, once you get this number here, it's okay to use it in the calculations. It's not introducing a huge error here. We only have one level of approximation. So you could certainly use this number when you want to consider the interest. So again, less interest, higher monthly payment. Again, you can make certain adjustments so you can avoid a high level of interest. And this is actually quite small when you think about the present value of a vehicle. So again, when we normally think of buying a car, we don't normally think of moving the payments forward yet. It might be 2 years into the payment of the vehicle, and then we say, I just won the lottery. Or you have some inheritance. It's like, well, I want to retire these payments. So you do the present value calculation. Usually, especially in my case, 2 years ago, I acquired a new truck. And so I was able to get a fairly good monthly payment. But again, I wasn't interested in this type of calculation. I just wanted to know what my payment would be. And so I've assumed that. And of course, once I complete the number of payments, then I get the title to my truck and I own it outright. Unfortunately, like I said before, we have to pay people or pay institutions money to use their money. Okay. And so once we've paid off the debt, then we own the vehicle outright. That is, we assume the title. Just remember, the title is still the property of the bank until you have paid all the payments. And then at that point, the title is transferred to you. Now, I want to look at one more example. Let's see here. This one actually is an interesting one. And I think it's something that will, number 5, that will ring true for many of you. Because we all think about purchases of cars, and we think about purchases of homes. Now, the purchase of a house for $120,000. Okay, so we have a down payment of $20,000, and therefore we want to finance $100,000. So again, when I acquired the truck, there were certain circumstances that were there, and I had a good down payment, so that was helpful. Down payments are always good if you have money to offer. So we're going to have a 30-year mortgage at 5.4% compounded monthly. So we want to compute what the payment's going to be. So just like when you think of purchasing a car, as I've said before, you purchase a home, having some money to put up front will save you interest in the long run. We don't always have that. Certain circumstances won't allow it, but it's certainly to your advantage. So we want to know what the payments are going to be. So we need the present value of $100,000. So now, again, M is 12, N is just MT. So we have 12 times 30. So in this particular case, we have a 30-year mortgage. We have 12 years. That's 360. That is 3 times 12 is 36. Tack on a 0. You have 360 payments. Yes, maybe 15-year mortgage might be something you want. But again, 30-year mortgage, that's also very popular. Now we have 5.4%. 0.4 is just 2/5. So 5 times 5 is 25 plus 2 is 27 over 5%. Divide by 100. Again, 27. 3 times 3 times 3. There are no 3's in 500, so we're stuck. So that gives us the annual interest rate. And now the periodic interest will just be the annual interest rate divided by 12. So again, note one thing that's interesting about this, and I didn't reduce this here, but when you think about it, we could have dropped one of the 3's out of this and made the number a little bit smaller. But I didn't do that when I wrote these notes. But you could do that, and there's nothing wrong with it. I think when I looked at this, 5 times 12 is 60. That's easy to do. But you could just reduce the 3's here, and that would give you 2,000 here, and it give you 9 here. That's an equivalent fraction. So smaller numbers, probably a little bit easier. So feel free to do that if you would like. And then 1 plus I, again, we have a common denominator of 6,000. 6,000 plus 27 is 6,027 divided by 6,000. That gives us the 1 plus I expression. And so now when we think about the payment, we simply have, in this particular case, we've got the periodic interest up top, but now in the denominator, we have the difference with the compound interest component. So again, notice, and this is where I do the reduction, which I could have been made easier had I done something up here. But now, of course, we just simply break these things down. Notice we've got 3 zeros here and 3 zeros here. So those zeros absorb. That's just a factor of 1,000. So we have 100 divided by 6. And now I've taken care of the 3 that exist here. So I did actually end up simplifying it. Notice the 6 is just 2 times 3. That absorbs, and we're just left with 50 times 9, which is 450. So eventually I was able to make the numbers more user-friendly. It doesn't matter how you work with the numbers. It's completely up to you. So if it's equivalent, it's fine. And now you can see that this is simplified. If you take the time to work with the arithmetic and factorize the numbers, then you can get much easier numbers to input. Again, be very careful. How you do it is completely up to you, but this is a clean way to do it. This is an exact expression. And so we have 450 divided by this difference. So what you can do is use your parentheses, 450, in parentheses 1 minus 6,027 divided by 6,000 raised to the negative 360. So again, if you want to go ahead and reduce this, as I said before, that would be fine. Now, this is where you have to think about technology. Raising real numbers to very odd powers like negative powers, that's something that requires an infinite series. And so that's where the beauty of the calculator comes in. This is not something that you would want to try to do by hand unless you had tables and a slide ruler. So the key here is that this is where the technology comes into play very, very handsomely. In finite mathematics, before the technology was as plentiful as it is, as ubiquitous as it is, you had tables in your finite math book that you used. And just like the kids taking trigonometry, they had tables of calculations for the trig functions because, again, the fancy little nifty calculators weren't available. So now when you do this calculation, you get a payment of $561 with some decimals here of 53. So you can basically round to the nearest dollar, and that'll give you $562 as your monthly payment. And your monthly payment, there'll be 360 of them, and then you will own the house. Now, again, when you think about this, this is one of the things about owning homes and all, when you've got more money involved, that everyone's not always very aware of. So if you take this amount here and hit it with the 360, you get $2,002, 320. So, or excuse me, 2002 or 2000. Well, let me try one more time and see if I can get this. 202,320. That's a little bit better way. So again, we've got the 202, right, with the 1,000 and then the 320. So $202,320. Wow, that's a lot of money. So now when you think about this, finance $100,000, you got a hefty amount of interest here. Now, let me just say this. This is not bad interest rate. 5.4 is not horrible. Okay. It's not the end of the world. But, if you can improve on that, that would certainly cut down the interest. But as the numbers get bigger, the interest rate does make a difference. You often hear that homeowners will refinance. The bank will offer a refinancing transaction, which can lower the annual interest rate and lower your payments. That is often a thing, transaction that homeowners will take advantage of. I can remember my dad did it when I was young. So the key here is that when you think about refinancing a particular transaction, you have that ability to be able to do. So let's just see what we have here. Let me go ahead and stop the share. I think we've lost, let's see the video here, just see if I can get that back. Let's see, share. Okay. Well, this is moving around. This is, let's see here. Yeah, this is working, but there's no video. Maybe the video's just dropped out. Well, you can hear me. I guess you just can't see me anymore. Well, ladies and gentlemen, that will do it. And we have again, present value of an annuity, and we have the future value of the annuity. And again, as you work through these, compare this to the compound interest problems you've already done, and I think you'll find that it's very user-friendly. So we're done with this. Enjoy your problems. Thank you very much.